just get stuck into it now. And again, thanks so much for everyone who's dialed in today. It's another really popular webinar. I can see there's well over 100 already in attendance. And just a reminder, if you've seen the poll, there is a live poll happening asking a question around how long do you think bioretention systems will last? If you haven't already done so, please put the answers in that poll. I can see 91 of you have already answered, and I'm going to show the results in about in a couple of minutes. So look, but I guess first and foremost, why are we even asking this question? It probably should be fairly self-explanatory in terms of the importance of actually knowing this answer. And it's bizarre how variable the answers are across the industry. But it's obviously critical to know how often we need to potentially rectify these assets and basically renew them. Obviously need to know how well they're going to work long-term as well. Also, it's worthwhile noting that a huge amount of money is being spent on them. So like with any sort of expenditure, whether it's a car or a house or something like that, or any sort of infrastructure, you kind of really want to know how long they last. And to give you an example, this is just a statistic from Health, Land and Water. Just in Queensland alone, they reckon around $3 billion worth of bioretention systems going to be put in Queensland alone over a 30-year period. And that's $100 million a year just in bioretention systems. So I think it's a pretty important question to know. And again, that's just in Queensland. I suspect it's more in Western Sydney and certainly in other parts of the country as well. So yeah, we're spending a lot of money on these assets. We should know how long they last. And like we often say, unless you've got data, you're just someone with an opinion. But a lot of people have opinions in this matter, and a lot of those opinions aren't based on much. So to give you an idea of opinions, I've obviously got the live poll happening, and I can see over 100 have already answered the question. Really interesting results. So if you haven't already done so, please complete that poll survey question. But whilst you're sort of doing that, if you haven't done so already, it's worthwhile noting that whilst I've got an opinion, I also have a conflict of interest. So Ocean Protect, the company I work for, I'm a principal environmental engineer at Ocean Protect. I have a conflict of interest. Ocean Protect, do bioretention systems and also alternatives to bioretention systems. So we do Filtera bioretention systems, and those images you can see on the bottom there, they're all Filtera bioretention systems. But also we make bioretention media. We make sandy loam media for conventional bioretention systems as well. But also we make alternatives to bioretention systems as well. And a lot of people would be familiar with our cartridge systems, for example. So long story short, I've got conflict of interest on both sides of the fence. But to mitigate that, at least in part, anytime I sort of refer to a study or a document in this talk, I'll provide the full reference. Yeah, sorry, Brian's going to ask a question. Thanks you, Brian. He says the poll question says should. Does it mean how long we want the system to last or how long we think they currently last? It's how long you think they will last. So just to clarify, hope that answers your question, Brian. It's not a question of how long they should last, is how long you think that they will last. If that helps. Just to clarify. So the question is, I'm just reading it now. How long do you think bioretention systems should last? As in, if it's appropriately put in the ground, for example. Okay. Hope that helps, Brian. Thanks for the questions. Keep them coming. On that note, though, I'm going to share the poll results. So I give people 5 more seconds to put in your answer. I can see there's already 108 answers. Going once, going twice, going 3 times. I'm going to end the poll, and I'm going to hopefully you guys can see the poll results. So let me just see if this goes. So I'm looking at the answers now. I'm not sure what you can see, but I've got out of 109 submissions, I've got 34% have said less than 10 years. 37% have said between 10 to 20 years. So roughly what's that? 71% have said less than 20 years. 14% have said 20 to 30, and 16% have said over 30 years. So yeah, interesting results so far. So I'll let you guys digest that for a sec. So just, 34% have said less than 10 years, 37 between 10 to 20. So like I said, 71% have said less than 20 years. And I guess what's that? 29% have said more than 20 years. Interesting. I'm going to stop sharing now. What I'm also going to show you is also, I actually asked the same question before. I gave basically a very similar presentation in the recent IECA Stormwater Queensland conference in Noosa just a few weeks ago. Same question. I asked to obviously a very similar crowd, bunch of stormwater engineers basically, and similar results. About what's that? 10% thought less than 10 years. 51% said 10 to 20. So what's that? 71% said less than 20 years, basically. So that's actually very similar to what we showed before. Sorry, Tom, did you have a question? Do you want to? Let me see if I can allow you to talk. Tom, did you have a question? You have to unmute yourself if you want to talk. There's a whole bunch of questions coming out already. Thanks for everyone for clarifying. Thanks, Courtney. Tom, do you want to say anything?
I would say that it can last indefinitely as long as the bioretention is properly maintained. So plants replace, filtration media replace, etc.
Cool. No, awesome. Thanks for that feedback, Tom. Quite a few people agree with you. Certainly not the majority. But thanks for that feedback. I'm gonna give you my opinion now, based on a whole bunch of data as well. So thanks for that commentary. It's worthwhile noting, to Tom's point. Sorry, Tom, I might have to. There we go. So just to clarify, there's obviously a lot of ways to kill a bioretention system. And this is straight out of Glenn Browning's presentation from, he's now at Brisbane City Council. He outlined 27 different ways you can kill a bioretention system, plants, and obviously the system itself. Whether it's too much water, too little water, dodgy maintenance, etc., a whole bunch of reasons. But probably the two most common reasons that I see cited in whether it be guidelines or other sort of documents is these probably two key reasons for failure. Number one, hydraulic conductivity, i.e. the system just doesn't drain very well at all. You get a whole bunch of ponding water, water doesn't drain through the filter media, so subsequently a whole bunch of water bypasses and doesn't get appropriate treatment. The second reason, commonly cited, is probably the more common one, is that after a while the system just stops removing pollution very well. So basically the system is like a sponge. So after a while that sponge reaches its capacity of absorbing pollution and just physically can't remove any more pollution anymore. So they're probably the two most common reasons that I see claimed. So they're probably the two main ones I'm going to focus on in terms of my review. In terms of opinions, there's a lot of them. Not just Tom's and the 130-something people that are dialing in today, but there's a whole bunch of industry guidelines around the planet which talk about how long a bioretention system might last. If I look at just across the ditch from Auckland, and I know a whole bunch of people from New Zealand are dialing in today, so greetings. You can read it for yourself. It's pretty confusing. They basically say every 5 years or so you need to dig it up, depending on a few things. But they also say that if it's badly constructed, you'll probably need to rebuild it within 2 to 3 years. But then they go on to say that it could last as much as 30 years if properly maintained. So they're spreading their bets, I guess would be a fair assumption there. So somewhere less than around about 2 to 3 years, or maybe more, maybe as much as 30 years. This is just one paragraph from one council guideline. Let's move on to what would be considered in many parts of the industry the Bible of water-sensitive urban design, how to model stuff in music. This is the e-water music manual, and they say basically every 25 years you probably need to replace the filter media. But then they also say there is great great uncertainty surrounding this period. That is true. But moving on, Melbourne Water. This is a leading authority in Victoria. They reckon, provided it is appropriately maintained, they should last at least 20 years. if I go to Blacktown City Council, I know there's a fair few Blacktown City Council staff dialing in today. This is straight out of their inspection and maintenance guidelines for WSIT assets. They say, and they're talking about vegetated assets, but that obviously applies to bioretention. They say it could last around 20 to 30 years if it's properly managed, but also could potentially last indefinitely, similar to what Tom was saying before. This is another paper out of the States. This is in relation to Filtera bioretention systems, which is a high-flow bioretention system, which I'll talk to in a sec. But they basically say, yeah, similar to Tom's claim, provided appropriate maintenance is performed, the systems should theoretically last indefinitely. And again, you can see I'm providing full references for these documents at the bottom of each of these pages as well. And again, the slides will be available on the website, so you can do your own research as well after today. Probably a really key document that is widely used across Australia is the CRC for water sensitive cities adoption guidelines for stormwater biofiltration systems. They say, in general, they should be expected to last, this is bioretention systems should be expected to last about 10 to 15 years. Now, one thing that I will give credit to here is that they at least provide a reference. This is a Belinda Hatt study from 2011, and, amongst other sort of documents, and I'm going to refer to that very shortly as well. So yeah, key documents basically saying 10 to 15 years. But what about data? I'm not so much interested in opinions most of the time, but I certainly value the feedback I've had today. But I'm going to show you a whole bunch of data around this issue. But it's also worth noting before I start is that there's actually a lot of, there's or at least seemingly, as per this paper, straight out of the Journal of Sustainable Water in the Built Environment, they basically say, yeah, this type of research around bioretention longevity is actually lacking. Most of the studies that we have seen in the literature are basically using column studies, like laboratory-based studies, or focusing performance testing on quite recently constructed bioretention systems, like less than 3 years old. So it's a real unknown as to whether that's actually appropriate in terms of assessing bioretention longevity. But despite this claim, I took it on board and tried to dig up as much research as I possibly could. And that basically sent me in all different directions, including lab studies and real-world studies across the planet. So first up, I mentioned that Belinda Hatt study before from 2011. And this is what the CRC for water sensitive cities guidelines refers to in relation to that general statement around it. They should last 10 to 15 years. That is based on this study. And as per the study, it's available online. They did show quick breakthrough of zinc, which is a heavy metal that's quite hard to absorb, or at least long term, because it's probably one of the first heavy metals to break through, i.e., go through the system. But they also claim that after about the equivalent of 12 to 15 years of operation, heavy metal concentrations exceeded guideline levels for ecology, and also cadmium levels exceeded the guideline levels for human exposure as well, based on land use for parks and recreation, open space, etc. Okay, and look, that's fair. Okay, but there's a big but to this study. First up, it is a lab study. So they're dosing synthetic stormwater. They're dosing synthetic stormwater over a very, very short period, 11 to 13 weeks of dosing, which they claim is the equivalent of 15 years of operation. And there's a real question mark on that, but I'll come to that later. Also, it's worthwhile noting that the filter media had very, very low organic carbon in it, like less than 0.005%, which is really, really low. And there's no vegetation in the filter media. So there's basically no life in the soil and the vegetation community in this lab study at all. Another key thing that I think has been completely ignored is that this study uses a filter media depth of 6 centimeters. Now I'm going to say that again. The study used a filter media of 6 centimeters depth. So not 50 centimeters or a meter that we see in most of our bioretention systems, but 6 centimeters. And obviously, that 6 centimeter of surface accumulation can be very easily removed. In fact, it's probably recommended that it is removed every so often. Also, finally, bioretention systems aren't parks or sporting fields. So I think the risk or at least the frequency of human exposure is very, very low. So I'd really question the applicability of those guidelines that this study refers to, and subsequently was adopted by the, water sensitive cities for, the CRC for water sensitive cities. Again, if you're keen to look into that study further, full references there as well. I'm going to look at a few other lab studies recognizing their limitations. This is a study that's out of the Canadian Journal of Civil Engineering. They looked at synthetic stormwater as well, equivalent to 20 years operation, 8 columns, decent depth and vegetation. And what they showed was actually effluent concentrations of pollutants decreased across the monitoring period. So basically, as the systems got older, the pollutant concentrations, the effluent concentrations decreased over time, which basically means the system is working better as it ages. Having said that, they also, this study is very clear or upfront in that in stating that there's a big limitation to this study or any lab study, and they say it here: the application of a large volume of runoff over a relatively short period of time does not mimic actual long-term operation, especially intermittent nature of rainfall events. It can be considered a worst-case scenario that tests these sort of studies. So they're saying here that this sort of study, this synthetic stormwater dosing over a very short period of time, as per the HAT study, is basically a worst case scenario. So it's worthwhile noting that these lab studies have very limited use. They're interesting and can be used for providing some sort of indication of lifespan, but certainly you really need to look at where basically the rubber hits the road in terms of the real world performance studies. And that's what I'm going to talk at now. So obviously there's a whole bunch of really good examples of bioretention systems. This is the Hoyland Street bioretention system out of Bracken Ridge. This is a photo just taken a couple of weeks ago. This is 22 years old now. Still looks okay. It probably doesn't get really any significant maintenance at all from councils. This is owned by Brisbane City Council, but it still seems to be working okay, or at least functionally, visually, it seems okay. Equally, there's a whole bunch of Filtera bioretention systems. Like, for example, this one these are in Australia. This is the first one built in Western Sydney in January 2018, so 5 years ago. That's what it looked like day one. This is what it looks like basically now, 5 years later. Equally, there's a second system out at Warwick Farm. This is in Western Sydney. This is it day one after it was first planted out. So you can see the vegetation, very small trees. There's diversity of vegetation, but generally fairly small plants. That was a photo 5 years ago, and this is what it basically looks like now. So this system is fully established, has only maybe been maintained once or twice, but certainly is functionally or visually looking really good. This is the same system from a different angle, just to show you the sort of mix of vegetation we've got here, and obviously the growth of vegetation. But obviously there's a whole bunch of systems that aren't so good, even systems that aren't very old at all, whether that's because of the vegetation's died off or the system's clogged with sediment and physically can't drain, like that one on the top right corner in the Redland Shire. But look, I'm sure you guys have seen your own share of I guess, poorly looking bioretention systems. Not that any of you guys have designed ones that aren't functioning very well. I'm sure we're all wonderful bioretention designers, etc. But obviously there's a whole bunch of bad examples. Some more data. So this is a study that was done a few years ago. The study on the data on the left is from Moreton Bay Regional Council. This is provided by Jonathan Whitcomb, who was the asset manager at the time for Woodford Systems. These are basically something like 380 bioretention systems owned within Moreton Bay on the left-hand side. And basically each of them got a IPWAQ condition assessment rating. So green is good, grey is average, and poor and very poor basically means the system needs significant rectification works. So basically 17% of all the 380 bioretention systems at the time in Moreton Bay needed some significant rectification works. The council on the right, which I won't name, fairly large number of bioretention systems, and long story short, they assessed that 22% of their bios were needing significant rectification works, basically needed to be dug up and started again. Some more studies. So this is straight out of North Carolina by Bill Hunt, etc. This is a study. This is a two-part study. They monitored a bioretention system shortly after it was constructed, about 2 years after it was constructed, and then they went back. 15, 16 years later, and to see how it performs. It actually was leaching nutrients at the start in the first part of the first study, but then when they went back, the system was actually working better. So over those several years of operation, the data showed that the system has actually improved its stormwater treatment performance. And they say here, if designed, built, and maintained correctly, bioretention appears to provide, sustained treatment for nitrogen and phosphorus for nearly 2 decades and likely longer. Interesting. Another study, this is out of Germany, would you believe? 22 bioretention systems, a whole bunch of land use types between 11 to 22 years of operation. They assessed the hydraulic conductivity of these systems and also assessed the heavy metal concentrations. Long story short, the hydraulic conductivity was fine. It showed no significant deterioration in hydraulic conductivity. The heavy metal concentrations were a little bit high in the surface layer of the filter media, but mainly around the inflow points. And basically, as per here, they mostly the heavy metal concentrations basically reach background or initial conditions after about 30 centimeters of depth. So, long story short, they were seemingly working fine in terms of hydraulic conductivity and no significant heavy metal contamination. They do provide a recommendation here in terms of just, every 20 to 25 years, just scrape off that the first sort of 1 or 2 centimeters of the filter media. And also they recommend to help to maintain the longevity, to try to spread out the water distribution over the surface of the filter media. So instead of just a single inlet, trying to get water across the whole area, which is very difficult, try to ensure appropriate flow distribution. And I'll show what that looks like in a second. Another study out of the Villanova University in Pennsylvania. This is an 8-year monitoring study, and they looked at orthophosphate concentrations. Now, why that's particularly interesting is the one pollutant that I generally hear claimed that you're going to hit your absorptive capacity is phosphorus, but you can see here after 9 years of performance monitoring, the bioretention system showed no sign of decreased orthophosphate removal. So it's not getting any worse at all. No significant decline in performance. And they showed that there's a little bit of saturation in the upper layer of the filter media, but certainly not in the deeper layers either. So again, the system is maintaining its stormwater treatment performance, i.e., doesn't seem to be dying. I'm going to look at Filterra bioretention studies now, and I've got quite a few. And this is an example of a Filterra bioretention system here at Silverdale. Why I'm particularly interested in showing these studies is, number one, there's a lot of data for Filterra bioretention, but number two, these systems treat a lot more water per unit area. So subsequently can be 3 to 5 times smaller than a conventional bioretention system. So this one, for example, at Silverdale, this would have been 5 times bigger if it had been a conventional bio, but because it treats water at a higher flow rate, it can be a lot smaller. But subsequently, the hydraulic loading rate is obviously a lot higher. So subsequently, if that's the case, and if bioretention systems did have a limited lifespan, surely you would see an earlier death in Filterra bioretention systems in particular. But do we see that? Let me show you. This is a study recently released by Contech in the States. They looked at 3 Filterra bioretention systems that have been in the ground for several years. I think at the time of monitoring it was between 11 and up to 6 and up to 13 years of operation. Long story short, the study is readily available. No decline in stormwater treatment performance and no reduction in the hydraulic capacity of the system. So long story short, no decline in performance. So no indication that the systems are going to die anytime soon. And now you can look at the individual studies and look at the individual systems in a lot more detail. This is the first one out of Virginia Beach, 9-year monitoring period, 92 sampling events. So a lot of data, really high pollution removal in terms of TSS, TP, and TN. So efficiency ratio, for people wondering what ER is, it's efficiency ratio. It's a ratio between effluent and influent concentrations, just a way of expressing concentration reductions. So long story short, consistently high performance. This is the second one out of Maryland, Baltimore, installed in 2005, 3-year monitoring period, 24 events, all high removals of TSS and heavy metals, etc. Equally at Virginia, again, installed in 2005, up to 11 years old by the time they finished the 8-year monitoring period. No decline in performance, really high rates of TSS and heavy metal removal. And look, if you're a nerd like me, you can look at all the data in a lot more detail. Again, it's readily available in the documentation. But long story short, we're seeing no decline in performance. Effluent concentrations, if you thought it was hitting its absorptive capacity, you would probably see an increase in the effluent concentration, for example. But we're not seeing that at all. We're seeing really consistent stormwater treatment performance over several years of operation. Western Sydney. So this is a study that I referred to a few times in previous Ocean Protect webinars. There's a published paper on it, etc. This is a system that is a Filterra bioretention system. The cabinet behind you, behind it, is a whole bunch of it's basically a house for a whole bunch of very fancy monitoring equipment to take influent and effluent samples, measure rainfall, measure flow, a whole bunch of stuff. It's been in the ground since April 2018. We've now been monitoring it for 5 years, and we've got 55 qualifying events. So there's a lot of data. Long story short, no reduction in performance, no reduction in infiltration rate, etc. And now I do have a lot of data on this, and it's hard to show it, but I'm going to try and do my best to show that data now. So if I look at the establishment period. So this is the first 12 months of the system after it was installed. So this is when the system's basically quite young. It's not necessarily handed over to the asset owner or whatever, just like a typical establishment period for a bioretention system. There was 10 events monitored. You can see all the different analytes here. So TSS, dissolved phosphorus, total phosphorus, NOx, ammonia, dissolved inorganic nitrogen, total kilogel nitrogen, total nitrogen. Generally, people are interested in the TSS and TP and TNs, which I've highlighted there. I've got concentration efficiency ratio here, median concentration reduction, and then load removal here. You can see the removal rates. For TSS, 78%, TP, 66%, TN, 46%. So this is the first 12 months. If I look at the more recent period, now this is a very solid set of data over about a year or so, 16 events. Long story short, you can see that the system has actually improved its performance. So if I just go back to the previous slide, that's 78, 66, and 46. It's gone up dramatically to 96, 95, and 72. So really, really good removals. Certainly no decline in performance. If anything, the system is improving its performance as it gets older. So in conclusion, the long-term data is pretty self-explanatory. The long-term real-world performance monitoring data of both conventional systems and Filterra bioretention systems demonstrate no significant decline in stormwater treatment performance or any significant decline in hydraulic conductivity. So I'm going to agree with Tom here, and I think it was about 10% of the attendees. If designed and installed, established and maintained correctly, the bioretention media and vegetation environment is likely to provide a sustained stormwater treatment function indefinitely. Now, I recognize that's a big if. So if it's designed, installed, and managed properly, these systems should last indefinitely and perform really well indefinitely. But again, that is a big if. And I'm going to come back to that in a sec. There are a couple of key unknowns. Number one, obviously bioretention systems is more than the filter media and vegetation. There are other components. I don't know how long they're going to last. You'd expect them to last a very, very long time, particularly if they're underground, I would have thought, not exposed to the elements or at least sunlight. But I'm not sure. I'm not sure if that's ever really been assessed. The other key unknown from my perspective is the impact to bioretention ecology. Now, I wouldn't have ever really thought about this as a key issue 6 months ago, but there was a study by the CSIRO team and a bunch of guys out at the university, I think WA. They looked at wetlands in Perth, stormwater wetlands, and they basically looked at the snake populations, the tiger snake populations, and they basically showed that PFAS and heavy metal contamination in the wetlands was basically causing the snakes ill health. So their ability to function, their body condition, etc., was impaired by pollution accumulation, particularly in relation to PFAS and heavy metals. Now, snakes are obviously an apex predator, but there are probably a whole bunch of other species that could be equally or worse impacted by pollution accumulation in the wetland environment. Now, it's a long bow, but maybe that might be an issue for bioretention systems as well, and the ecology that is attracted to these systems. Not sure. Something worthwhile investigating, certainly beyond my abilities, but hopefully there's a PhD student out there looking for something to study. So what are the implications of this, though? So I'm saying that these bioretention systems should last indefinitely. So what does that actually mean? So long story short, if we're designing these systems, or like basically long story short, if these systems should be designed, installed, and maintained to achieve what I'm going to steal Jonas's words here, to achieve a self-sustaining system that fulfills the obligation of a bioretention system with an emphasis on diversity. And again, if you're keen to know more about this, talk to the guy on the right, Jonas Larson. He's done a webinar on it recently, but I'm happy to put you guys in touch if you don't have his details. Long story short, design these systems and put them in the ground to be an ecosystem and outlive you and everyone you know. What are the implications for asset managers, though? So if bioretention systems are lasting indefinitely, how do asset managers, how should the asset managers appropriately manage them? The key recommendation is asset managers should not be planning to replace these systems just because of some perceived deterioration in stormwater performance. But having said that, they need to be appropriately maintained. A key maintenance intervention in particular is to make sure that accumulated solids is removed. So these systems are still going to capture and retain pollution. Now, there's a couple of ways of removing that solids. Ideally, from my perspective, you mulch the surface and remove it and replenish it, or you scrape the surface, the filter media surface, and remove that. Long story short, you apply an adaptive asset management approach. And Ben Panalera can talk about adaptive asset management to the cows come home, literally. So if you're keen to know more about that, please talk to Ben. But long story short, consistently with what Jonas was saying, they should be managed as ecosystems and should be subsequently, if you're doing that, you should be involving ecologists and traditional owners as well. What about designers? Now, I recognize I've got mainly designers on the podcast, on the webinar today, not the podcast. What should you do if you're a designer? First up, involve an ecologist. Secondly, aim to deliver ecosystem functions and services, and maybe consider the lifespan of other components. Maybe look to reduce your reliance on other components. Maybe, I don't know. But I think from my perspective, the key thing that designers should be doing is maximizing resilience. So there's a whole bunch of things you should be doing to do that. Reduce incoming pollutant loads. I think it's a mistake that we think that these bioretention systems can just take whatever pollution comes off an untreated catchment. Ideally, reduce pollution at the source or provide some sort of pre-treatment. Obviously, there's conflict of interest here. Ocean Protect does gross pollutant traps, but I think that's a key step to maximizing resilience. Secondly, ensure appropriate hydraulic design, making sure that flows are appropriately distributed, not just a single inlet. Eliminate base flows, but also make sure the system is offline, so you're not going to get a whole bunch of erosion and scour coming through the system because of high velocity flows. Thirdly, ensure the filter media is appropriately consistent with the specification. Now, at Ocean Protect, when we make Filterra media, for example, it's a very detailed procedure. It's a 25 QA/QC step. I don't see anything like that happening in the manufacturers of sandy loam media. But regardless, you need to make sure that filter media is appropriate. Also, in terms of vegetation, making sure there's a diversity of vegetation, and again, making sure that these systems can be appropriately maintained. Now, there's a whole bunch of information in the Water by Design guideline in relation to this, the improving the biology of the bioretention systems. I know the authors are actually tuning in as we speak, so shout out to Paul Dabowski and Ben Peneleric, but also there's a whole bunch of information in the Filtera Technical Design Guideline. Basically, all these things, in terms of maximizing resilience, we incorporate in Filtera bioretention systems. And just to show what that actually even looks like. So this is the Silverdale system I showed before. You can see here they've got multiple bubble up pipes to ensure a good flow distribution across the system. It is offline, so it takes low flows. The high flows are basically trundled through this high flow channel and not through the bioretention system. And also there's a diversity of vegetation, obviously, as well. That's the same system out at Silverdale, but just looking at a different part of it. So you can see, I guess, probably just shows the diversity of vegetation there. Still has lamandras, but if you look at some of our other systems, there's a real diversity of vegetation in these systems as well. These are out at Bells Creek or up near Caloundra. So you can see, I guess, the diversity of vegetation we're looking to put in these systems. And obviously, I showed this example before in terms of the Warwick Farm system. Again, you can see a real diversity of vegetation. You can see the mulch layer under in the understory of this system. So really good for retaining moisture within the filter media, acting as a pre-treatment. Even though the system hasn't been maintained I think it's got 1 or 2 maintenance interventions in 5 years. Highly resilient system. Seems to be working very well. That's it for me. I can see a whole bunch of questions in the Q&A. So if you do have any questions, please put them in the Q&A. I'm going to try and get to them now. I can see a whole bunch of commentary as well. I'm going to stop sharing so I can get a better idea of some of these. Well, sorry, Tom, you might need to mute yourself because I can see you. I'm just going to ask you to unmute. I might get that screen back, saved everyone looking at Tom's screen. Apologies, Tom. So questions. Again, I've got a bunch already, but if you've got any further, please put them in the Q&A panel. First up from Zul Hoke from, I'm not sure where Zul's from, but Zul asks, is it required to change the bioretention system after a major flood? Not necessarily. If I look at it might be easier if I show you the one I showed before, the Warwick Farm system at, where is it? This one here. This is actually right next door to the Georges River. And a couple of years ago, the Georges River literally overtopped into this system and deposited about 1 foot of mud across the surface of the mulch layer. Did we need to replace the whole thing? No, we just scraped the mud away and scraped the mulch away. We did hydraulic conductivity testing of the filter media. It was still draining really well. Again, it provided the system has appropriate resilience, particularly the application of mulch to help provide a screen for sediments and muds that can deposit in a flood event. You might not necessarily need to do so in terms of replacing the whole system. Thanks for the questions, Azul. Cool. Thanks, Courtney. You can see the poll results. Thank you. Michael Ward. Yeah, Michael Ward says, recognizing that council are unlikely to undertake maintenance and bioretention systems, shouldn't we be designing them for a reasonable lifespan? Look, I think I'd prefer recommending that councils just appropriately manage these systems. Now, that might be a stretch. And in the absence of appropriately frequent maintenance interventions, designers should certainly be trying to maximize resilience using the steps I recommended before. I hope that answers your question, Michael. Courtney Henderson, it seems based on the guidelines, the newer the guideline, the longer the lifespan for bioretention systems. Yeah, interesting, maybe. Yeah, well, I think the CRC for water sensitive cities one's reasonably recent. I think that was 2018. They were saying 10 to 15 years, whereas e-water was a 2014 guideline. So I was saying 25 years. So it definitely varies. I'm not sure if there's a pattern just yet. We'll see. So Brian Corrigan asks, so what are the requirements around disposal of filter media, which can contain excessive heavy metals, but is likely unknown what the actual concentrations are? Is the filter media considered contaminated material? This is an easy thing to assess, Brian. You just take a sample and assess it for contamination. If it's obviously above a certain levels, you probably need to take it to a certain contaminated contaminated waste facility, but if not, it might be available to dispose of it in a landfill. I can provide a reference to that actually if you like. I think it's in a water by design guideline. If you email me, Brian, I can send you the exact reference. Thanks for the question though. Che McKenzie asks, what is the maintenance regime for the Filtera studies? Yeah, good question. The Filtera studies I referred to before, this is, I guess, the Contact paper here. I think it was pretty basic maintenance, like it's certainly not gold plated. And I think one or two of them got very, very little maintenance. So there certainly wasn't anything out of the ordinary. The key thing we recommend in terms of the maintenance of Filtera is just to replace the mulch, is probably the main one, every 1 or 2 years. Now, as per the Warwick farm system I showed before, that certainly hasn't happened more than maybe once or twice in 5 years, but it's still maintaining its longevity. But certainly, I'd probably expect the same thing for these studies. But again, the maintenance regime will actually be described here, but I don't think it's anything out of the ordinary. Courtney Henderson from ACOM says, great to see all this data. My PhD research indicated that microbial activity in the rhizosphere appeared to refresh the absorptive capacity of the media for phosphate and ammonia. Yes, thank you, Courtney. I do remember your PhD. So yeah, I think this data that I'm showing here certainly supports or is consistent with your PhD research. So I must admit I didn't actually find your PhD in the studies I did, Courtney. So if you can send me the link, I'd be more than happy to review it. Recognizing it was quite a few years ago now, not that long ago though. Another question for Courtney. Courtney says, presumably the microbes cleave off the nutrients, freeing up the absorptive capacity of the filter media. Therefore, it was concluded that maintaining the health of the rhizospheres was important. Yeah, possible. I think that's probably a factor, Courtney. So yeah. Thanks for that. Mark Ibrahim says, most systems you've discussed are for larger scale developments. What studies have been done on small scale residential rain gardens that a mum and dad are expected to maintain and do not? What is the lifespan when no maintenance is done? It's a great question. As per my commentary, I think the lifespan is certainly dependent on the appropriate management of these assets. It's just like a car. If you don't maintain your car, you'd expect it to have a limited lifespan. So I don't think there's been much in that way of data to support. Sorry, I backtrack. I don't think there's been very many studies in terms of, or any studies in terms of, can a system last without any maintenance? I remember there was the zero asset maintenance Worsted ideology in Victoria, kicked around a few years ago. To the best of my knowledge, I think that it was basically mothballed, because I think fundamentally these systems, whatever it might be, whether it's a GPT or a wetland or a bioretention system, all assets need appropriate maintenance, and you'd expect a limited lifespan when no maintenance is done. Paul's given a link to Paul Dabowski has given a link to the water by design filter media specs, which improve the biology of bioretention, which I'll put in the chat as well, just for everyone. Let me just do that now. Paul, this is from Paul Dabowski, the water by design document I referred to before. There's a bunch of, if you've got, that's all the questions I have. If you've got any further questions, cool. There's nothing in the chat. So if there's no further questions, I'm happy to leave you guys to it. But just as a reminder, if you do want to talk further about bioretention longevity, feel free to reach out. Sorry, I spoke too soon. There's questions coming in already. Ben Peneleric, Yeah, good point, Ben. Ben says there are bioretention systems over 20 years old that are still performing well with little to no maintenance. They all have trees and ground covers. I don't think there's many, Ben, that are over 20 years old that are still performing well. Certainly the Hoyland Street one is 22 years old. That's the second oldest bioretention system in Australia. And like you said, that seems to be working, or at least visually functioning very well. I'm just going to try and show you a picture of what I mean. So give you an example. Where is it? This is the Hoyland Street bioretention system at Bracken Ridge. You're welcome to go out and check this one out yourself if you like. It's readily available to the public. And this is 22 years old. This is the second oldest system in Australia. This has got very little maintenance, to the best of my knowledge. I know Brisbane City Council have done a few studies on it, looking at hydraulic conductivity and performance. And to the best of my knowledge, the data shows that there's no deterioration in performance. So I think, Ben, your commentary around diversity of vegetation is important. Yeah, the systems with tree coverage and ground covers are going to be more resilient. And certainly the ones I've shown or looked at certainly have those attributes. Abishka, I hope that helps, Ben. Feel free to chime in for more commentary as well. Abishka Johar, sorry, I'm going to mispronounce it. Bihesek. Sorry, I probably mispronounced your name. They ask, does droughts affect the bioretention systems? It's a great question. Yes, obviously any vegetation needs water, but it certainly depends on a whole bunch of other aspects as well, particularly the ability of the system to retain water. So to give you an example, this one out at Western Sydney, this was built in, you can see here, it was put in 2018, received no supplementary watering, and it basically survived a pretty extensive drought period in Western Sydney. Now, the reason why I think this was actually able to work and thrive quite well is because of two things. Number one, there's a decent amount of organic matter in the filter media. Secondly, there's a really good layer of mulch on the surface. For Filtera systems, we use a 75mm depth of double shredded hardwood mulch, which acts to help protect the filter media, but also helps retain water within the filter media. But also, we do prefer to put in species basically that can handle extended dry periods as well. And they're basically the same plants that you would probably see in a recommended list of standard conventional bioretention systems as well. Ben Peneleric says, oh yeah, Wakeley bioretention system. Yeah, I'm not sure how old that one is. That might be upwards, that might be nearly 20 years. Yeah, cool. Any final questions, guys? If you don't, that's cool. If you do have any further questions, you'd like more information as to what I've talked about today, feel free to reach out to me via my contact details here. The slides and recording will be made available online on the Ocean Protect website under the webinars tab probably tomorrow, and that'll include all the references to all the studies that I've referred to today as well. Cool. But if there's no further questions or comments, Ben also asks, can you share the presentation? Great work and interesting to see how well treatment performance has held up. Yeah, cool. Ben, certainly, yeah. I will share this entire recording and the slides on the Ocean Protect website under the webinars tab, as per all our webinars. Cool. Well, there's no further questions or comments. Awesome. Great. Well, thank you so much for the feedback. If you've got nothing further to ask me or say, I'll let you guys get on with your day. But thanks so much for joining today, and I hopefully see you in person sometime soon.